The Artemis II prelude. Beyond the safe harbor on December 7, 1972, the Apollo 17 capsule re-entered Earth's atmosphere, marking the end of the last crewed mission beyond low Earth orbit, LEO. More than 50 years have passed since that moment, half a century during which humanity has launched into space hundreds of times, yet each time, we remained within a narrow band just 400 to 450 kilometers high, where the International Space Station, ISS, resides. This is not a coincidence, it is a conscious choice dictated by a simple truth: low Earth orbit is a safe harbor. Everything beyond it is the open ocean. To understand the scale of this difference, consider this. The ISS orbits at an altitude of approximately 420 kilometers. That is roughly the distance between London and Paris, a distance you could drive in a few hours. The Moon, however, is 384,400 kilometers away, nearly 1,000 times farther. If the ISS is like swimming in a pool with the edges always in sight, a lunar mission is like crossing the Atlantic on a wooden raft. But it isn't just about the distance, it's about what lies between. The Van Allen radiation belts, the invisible wall. In 1958, just months after the launch of the first American satellite, Explorer 1, physicist James Van Allen discovered something alarming. The Geiger counters on board detected regions of intense radiation encircling the Earth like giant, donut-shaped clouds. These were the Van Allen radiation belts, traps of charged particles, protons and electrons, captured by Earth's magnetic field. There are two primary belts. The inner belt, 1,000 to 6,000 kilometers, contains predominantly high-energy protons with energies up to 400 MeV, megaelectron volts. The flux density reaches 10-4 particles per square centimeter per second. The radiation dose here can exceed 10 MSV or hour, the equivalent of an entire year's worth of a nuclear power plant worker's allowable dose, absorbed in just 1 hour. The outer belt, 13,000 to 60,000 kilometers, less intense but far more vast. It contains electrons with energies of 0.1 to 10 MeV and is highly dynamic. Its intensity surges violently during geomagnetic storms. The ISS flies underneath the inner belt. It sits in a narrow safety zone where Earth's magnetic field is still strong enough to deflect most cosmic rays, but the radiation belts haven't yet begun. Astronauts on the ISS receive about 150 to 200 MSV per year, 50 to 70 times more than the average person on Earth, but within manageable limits. Artemis II will cross both belts twice, once on the way out and once on the return, and that is only the beginning. The contrast, the ISS cocoon vs. the lunar abyss. Life on the ISS, despite its complexity, exists within a relative comfort zone. Radiation, partially shielded by Earth's magnetosphere. Temperature, stabilized by massive thermal control systems. Emergency return, a Soyuz or Crew Dragon capsule is always ready. The return time is roughly 3.5 hours from undocking to touchdown. Communication, near instantaneous, via the TDRS satellite network, with a latency of less than 1 second. Psychology, Earth is visible every 90 minutes. It is massive, filling half the sky. Artemis II is a completely different reality. Radiation, full exposure to solar proton events, SBEs, and galactic cosmic rays, GCRs, no magnetic protection. Temperature, extreme swings from plus 120 degrees Celsius in direct sunlight to minus 150 degrees Celsius in the Moon's shadow. Emergency return, non-existent. If the service module engine fails on the outbound leg, the crew is lost. The minimum return time is 4 days. Communication, latency increases to 1.3 seconds at the Moon. It is severed entirely whenever the ship is behind the Moon. Psychology, Earth shrinks to the size of a bright star. For the first time in 50 years, humans will see the entire globe fit into a single window. This is not just a more difficult mission. It is a qualitative leap into a realm where nature never intended humans to survive. Chapter 1. The Gravity Well and the Free Return Trajectory. Escaping the well, the physics of the SLS launch. To reach the Moon, the Orion spacecraft must first break free from Earth's deep gravitational well. This requires the Space Launch System, SLS, the most powerful rocket built since the Saturn V. SLS Block 1 specifications. Height: 98.1 meters, equivalent to a 32-story building. Liftoff mass: 2,608 tons. Thrust at liftoff: 39,140 knots, kilonewtons. Payload to translunar trajectory: 26 tons. For comparison, the Space Shuttle's engines produced 30,160 knots. The SLS is 30% more powerful. The launch sequence: simplified. T6.6 seconds. Ignition of the 4 RS-25 engines at the base of the core stage. These are modified shuttle engines, each generating 1,860 knots of thrust at sea level, burning liquid hydrogen and liquid oxygen. The combustion chamber temperature reaches 3,300 degrees Celsius, higher than the boiling point of iron. T0. Ignition of the 2 solid rocket boosters, SRBs. Each contains 500 tons of ammonium perchlorate, oxidizer, aluminum powder, fuel, and a binding agent. The combined thrust of the SRBs is 28,600 knots. Once ignited, these boosters cannot be turned off. They burn for 126 seconds until the fuel is exhausted. T plus 0 to T plus 126 seconds. Vertical ascent with acceleration increasing from 1.3 g to 4 g. The Orion crew is crushed into their seats with a force 4 times their body weight. A 70 kilograms astronaut feels like they weigh 280 kilograms. Breathing becomes difficult as the chest cavity is compressed. At an altitude of 45 kilometers, the boosters separate via explosive bolts and fall into the Atlantic Ocean, later retrieved for analysis. T plus 126 to T plus 510 seconds. Only the 4 RS-25 engines remain active. Acceleration gradually climbs to 5.5 g as fuel burns off and the rocket's mass decreases. This is the physiological limit for humans. At 6 g, the risk of GLOC, G-induced loss of consciousness, becomes critical. T plus 510 seconds, minus 8.5 minutes core stage separation. Altitude: minus 160 kilometers. Speed: minus 7.5 kilometer ARS. Orion remains attached to the Interim Cryogenic Propulsion Stage, ICPS, which houses a single RL-10 engine with 110 knots of thrust. T plus 540 to T plus 1100 seconds. The ICPS pushes Orion into a circular 185 kilometers parking orbit. The crew performs system checks. For the first time, they experience weightlessness. Stomachs rise toward throats, and bodily fluids shift toward the head, causing facial swelling and nasal congestion. Translunar injection, TLI, the second fiery kick. Approximately 1.5 to 2 hours after launch, as the ship passes over the Pacific Ocean, the command comes for the most critical maneuver, translunar injection. The RL-10 engine ignites again for 18 minutes, accelerating the 26-ton Orion Plus ICPS stack from 7.7 kilometers per second orbital velocity to 10.9 kilometers per second. This additional 3.2 kilometers per second is the delta V, the change in velocity required to enter a lunar trajectory. This is where gravitational magic happens. Orion is no longer moving in a circle around Earth. It moves along an elliptical trajectory, the furthest point, apogee, of which touches the Moon's orbit 384,400 kilometers away. The physics of the free return. After TLI, Orion is on a hybrid trajectory, designed with brilliant simplicity. If the service module's engine fails completely, the spacecraft will automatically swing around the Moon and return to Earth without any additional maneuvers. How it works. Outbound trip, days 1 to 3, the ship moves against Earth's gravity, gradually slowing down. Speed drops from 10.9 kilometers per second to minus 0.8 kilometer ARS at the edge of Earth's sphere of influence, minus 60,000 kilometers from the Moon. Lunar capture. Day 4, as Orion enters the Moon's gravitational sphere, lunar gravity begins to accelerate the ship. Velocity increases to minus 2.5 kilometer ARS. Flyby. Days 4 to 5, the ship passes behind the Moon at a minimum altitude of minus 130 kilometers over the far side. lunar gravity bends the trajectory by -240 degrees, like a slingshot, flinging Orion back toward Earth. Return, days 5 to 9. Earth's gravity accelerates the ship once more. By the time it hits the atmosphere, velocity reaches 11 kilometers per second, Earth's escape velocity in reverse. The critical margin. The free return trajectory only works if TLI is performed with a precision of 0.01% in speed and 0.1 degrees in direction. An error of just 10 meters per second means the ship misses the moon by 5,000 kilometers, causing the return path to miss Earth entirely. To fix this, the crew performs small TCMs, trajectory correction maneuvers, using the service module's thrusters. The service module, the only life insurance. The European Service Module, ESM, is a cylinder 4.5 meters in diameter and 2.7 meters high. Built by the European Space Agency, it contains AJ-10 main engine, 26.7 knots thrust, 319 second specific impulse. It burns monomethyl hydrazine, toxic fuel, and nitrogen tetroxide, even more toxic oxidizer. This is a hypergolic mixture. It self-ignites on contact, requiring no spark. 8 auxiliary thrusters, 490 N each, 4 mid-sized corrections. 24 reaction control system, RCS, thrusters, 220 N each, for precise attitude control. 4 solar arrays, 60 square meters total, providing 11.2 kilowatts of power. Fuel, 8.6 tons, nearly 1/3 of the ESM's mass. If the AJ-10 main engine fails after the lunar flyby, the crew might attempt to use the 8 auxiliary thrusters for a critical correction. However, their combined thrust is only 3.9 knots compared to the main engine's 26.7 knots. If the required correction exceeds -50 meters per second, typical for large deviations, the auxiliary fuel won't be enough. The result? The ship would miss Earth and enter an elliptical orbit around the Sun. The crew would die of oxygen depletion, -21 days, somewhere between the orbits of Earth and Venus. This is not a theoretical danger. This exact scenario nearly occurred on Apollo 13 when an oxygen tank explosion disabled the service module. That crew only survived because the lunar module had its own backup engine. Artemis II has no lunar module. There is only one engine and one hope. Chapter 2. The Invisible Killer, Radiation. 2 enemies, SPE and GCR. Beyond Earth's magnetic shield, the Artemis II crew will face 2 forms of radiation, each lethal in its own way. 1. Solar particle events, SPE. The Sun is not a stable light bulb. It is a thermonuclear reactor convulsed by magnetic storms. When the Sun's magnetic field lines twist and suddenly snap, they release energy equivalent to billions of megatons of TNT. This is known as a solar flare. Class X flares, the most powerful, accelerate protons to energies of 100 to 500 MeV and blast them into space as a directed stream. These protons travel at 30 to 50% the speed of light, approx. 100,000 kilometers per second, reaching the Moon's orbit in just 30 to 40 minutes after the flare occurs. Radiation dose from a major SPE. An event in August 1972, between the Apollo 16 and Apollo 17 missions, generated a proton flux that would have delivered 400 MSV to the skin and 1 to 3 sieverts, to the blood-forming organs of an unshielded astronaut in just a few hours. A dose of 3 sieverts causes acute radiation syndrome, ARS, with a 50% probability of death within 30 days, LD 50/30. Symptoms begin within 2 to 3 hours, nausea, vomiting, and diarrhea. After a week, hair loss, internal bleeding, and the destruction of bone marrow follow. 2. Galactic cosmic rays, GCR. GCR is background radiation that constantly permeates space. Its sources are supernovas, pulsars, and black holes, objects that accelerate atomic nuclei to energies of 1 to 10 GeV, gigaelectron volts, and higher. A typical GCR particle is an iron nucleus, Fe56, traveling at 99.9% the speed of light. The kinetic energy of a single such particle is comparable to a 9 mm bullet, but compressed into the volume of an atomic nucleus. GCR dose in deep space. The dose is approximately 0.5 to 1 MSV per day, or 150 to 300 MSV for the 10-day Artemis II mission. For comparison, the annual allowable dose for a nuclear power plant worker is 20 MSV. The Artemis II astronauts will receive the equivalent of 7 to 15 years of nuclear plant work in just 10 days. Protection, aluminum, water, and the geometry of Despair the Orion hull crew module outer shell, 4 mm aluminum alloy, micrometeoroid and debris protection, Whipple shield multi-layered fabric of Kevlar and Nextel, equivalent to 10 mm of aluminum inner liner, 3 mm composite panels, total shielding, equivalent to approximately 20 mm of aluminum, density 2.7 g/cm cubed, aerial density $5.4 a text, g/cm, $2. This sounds encouraging until you understand the physics of the interaction. The shielding paradox. When protection kills, there is a fundamental problem with shielding against high-energy cosmic rays. When a GCR particle, such as an iron nucleus with an energy of $10 text, GeV, collides with an aluminum atom in the ship's wall, it doesn't simply stop. It fragments. A single iron atom shatters into dozens of lighter fragments, nuclei of silicon, magnesium, oxygen, protons, and neutrons. These fragments scatter in a cone, like shrapnel from a grenade. This phenomenon is called nuclear fragmentation or secondary radiation. The paradox. Thin shielding, $5 a text, 10 text, g/cm, $2, generates secondary radiation that can be more biologically hazardous than the original particle because the fragments have a higher linear energy transfer, LET. Ideal protection would require a thickness of $30 a text, 50 a text, the g/cm, $2, 15 to 25 centimeters of aluminum or 7 to 12 centimeters of polyethylene. However, this would add several tons of mass to the spacecraft, an unacceptable trade-off. The Orion Compromise. Base hull protection, $5.4 a text, the g/cm, $2 localized protection, creating a refuge inside the spacecraft. The Storm Shelter Protocol, a biological shield of water and food when mission control, or onboard automated detectors, registers a powerful solar flare. The crew receives a 20 to 30 minute warning before the proton storm arrives. This is their window for survival. The sheltering procedure, Step 1. Identification of the refuge, 2 minutes. The center of the Orion crew module, the area between 2 rows of equipment lockers. The volume is approximately 2 cubic meters, the size of a telephone booth. 4 people must squeeze into this space. Step 2. Building the protective cocoon, 15 minutes. The crew moves all available dense materials around the refuge. Water tanks, $4 a times 25 a text, liters, equals 100 text, kilogram. Water is an excellent shielding material. The hydrogen in $H_20 effectively slows down protons through elastic collisions. Aerial density, $10 text, cm of water, equals 10 text, the g/cm, $2. Food containers, -40 kilograms total canned goods, dry rations, any mass helps, soft gear, sleeping bags, clothing, packaging materials. These are used to plug gaps. Step 3. Sealing the shelter, 5 minutes, closing the improvised refuge with protective panels. The crew remains inside until the proton flux subsides, usually 6 to 12 hours, and in the worst case scenario, up to 48 hours. Effectiveness. In an ideal configuration, the shelter provides an additional $15 text, 20 a text, g/cm, $2 of protection in critical directions. This reduces the dose from a major SPE from $3 text SV to $0.5 a text, 0.8 text VSV $. This is still dangerous. Approx. 10% risk of acute effects plus 30% long-term cancer risk, but it is not immediately lethal. The problem: the shelter only protects against SPEs. It is largely ineffective against background GCRs because GeV range particles pass through $20 a text, GSCM, $2 almost unimpeded. Cellular genocide. What radiation does to DNA to grasp the true danger? One must descend to the molecular level. The mechanism of damage when a high-energy particle, an SPE proton or a GCR ion nucleus, passes through a cell, it ionizes atoms along its path, stripping away electrons and creating free radicals, particularly hydroxyl radicals $O a CDOT $. A single $100 text, MeV, $proton creates approximately 100,000 ionizations along a $1 a text, $, trajectory through tissue. These radicals attack the DNA molecule, causing single-strand breaks, SSB a break in one of the two helices of the DNA. The cell typically repairs these using the second strand as a template. About 10,000 SSBs occur naturally in every cell every day due to metabolic processes. Double-strand breaks. DSB both helices are severed within a few nucleotides of each other. This is a critical injury. The cell attempts to repair a DSB using non-homologous end joining, NHEJ, but this process is error-prone. The probability of incorrect repair is 15% cluster damage, multiple DSBs and chemical modifications of bases within 10 to 20 nucleotides. Such damage is almost impossible to repair correctly. A single GCR particle, an ion nucleus at $1 a text, GeV, creates 20 to 50 DSBs as it traverses the cell nucleus. The consequences: apoptosis. Programmed cell death. If the damage is too extensive, the cell receives a signal to self-destruct. This is a defense mechanism against cancer, but massive apoptosis in bone, marrow, intestinal epithelium, or nervous tissue leads to acute radiation syndrome mutations. If a cell survives with incorrectly repaired DNA, the mutation is passed on to daughter cells. Critical mutations in genes like P53, BRCA1 or 2, or RAS can lead to cancer 5 to 20 years later. Chromosomal aberrations, breaks and incorrect reconnectines of chromosomes. These are visible under a microscope as decentrics, chromosomes with 2 centromeres, or ring chromosomes. These cells are usually non-viable. The Artemis II calculation: over 10 days, the crew will receive -150 to 300 MSV from GCR and, assuming no SPE, an additional -20 to 50 MSV from passing through the Van Allen belts. Total dose, -200 to 350 MSV. This will increase the lifetime risk of death from cancer by -2 to 3% for each crew member. For context, the baseline risk of death from cancer in developed countries is -25%. The mission raises this to 27-28%. Does that sound acceptable? Perhaps, but this assumes no major SPE occurs. If it does, those figures are multiplied by a factor of 5 to 10. Chapter 3. Thermal extremes and the lunar shadow vacuum as the perfect insulator on Earth. We cool down or heat up via 3 methods: conduction, direct contact with matter, convection, movement of gas or liquid, radiation, electromagnetic waves, infrared radiation. In space, the first 2 do not work. A vacuum means there are no molecules to conduct or convect heat, only radiation remains. And this changes everything. The problem of solar heating: the solar constant at the distance of the Earth and Moon is $1,361 text, WM-2. This means every square meter of surface facing the Sun receives energy equivalent to a powerful space heater. Orion's cross-sectional area, facing the Sun -10 m², receive power, $13.6 text, kilowatt, $. For comparison, this is like 3 industrial hairdryers running continuously. If the spacecraft were a perfect black body, absorbing all radiation, the surface temperature would stabilize at a level where the power radiated equals the power absorbed, according to the Stefan-Boltzmann law. $T equals a left, or frac P, sigma A, O right, dash 0.25, $where $sigma equals 5.67 times 10-8, O text, W, M, 2 text, K, -4, Dollar is the Stefan-Boltzmann constant for a total radiation surface area of $50 a text, $2, the ship's total surface, and an absorbed power of $13.6 text, kilowatt, $T or approx 280 text, K, dollar or dollar plus 7 text, degree C. Does that sound comfortable? Not quite. This is an average temperature. The sun-facing side heats up to plus 120 text, degree C, dollar, while the shadowed side cools down to $-100 text, degree C, dollar. Active thermal control system, ATCS fighting entropy inside Orion. Humans and equipment generate $1 text, 2 a text, kilowatt, dollar of heat. Human metabolism $100 text AW, O times 4 text A people, dollar plus electronics. This heat must be removed. Otherwise, the internal temperature will rise by $1 text, degree C, dollar every 15 minutes until it reaches lethal levels. Orion's ATCS consists of 2 loops. 1. Internal loop, water-based, coolant, a mixture of water and glycol temperature, $4 a text, 16 text, degree C, dollar. Mechanism. Pumps circulate the liquid through heat exchangers in the cabin walls, absorbing heat from the air. Cold plates located under the electronics, liquid cooling and ventilation garments, LCVG, when the crew is suited up. The system removes up to 300 text, W, dollar of heat per person via tubes woven into their undergarments. Point 2. External loop, ammonia-based. Coolant, anhydrous ammonia, $NH_3. Freezing point, $-77 text, degree C, dollar, allowing it to function in deep shadows. Mechanism. Ammonia circulates through a heat exchanger to collect heat from the water loop and carries it to the radiators. Radiators, panels with a total area of $20 a text, $2 located on the exterior of the service module. They emit infrared radiation into the void of space. Radiator radiation power at a temperature of $40 a text, degree C, dollar, $313 text, K, $P equals sigma a times A a times epsilon a times T4 where of epsilon or approx 90 cents, the emissivity of specialized white thermal paint, $P or approx 5.67 times 10-8, O times 20 times 0.9 times 313 to 4 or approx 10 text, kilowatt. This is sufficient to dissipate heat from the crew and equipment while partially managing the solar thermal load. Nightmare scenario, 18 hours in the Lunar Shadow Day 5 of the Artemis II mission. The spacecraft enters the moon's shadow on the far side, sunlight vanishes, the temperature of the outer hull begins to plummet. T plus 0 minutes. Eclipse entrance. The ESM solar arrays stop generating power. The ship switches to its batteries, minus 12-hour reserve at full load. The radiators continue to emit heat into the void, but they are no longer receiving solar thermal input. T plus 30 minutes. Radiator temperature drops to 50 degrees C. The ammonia in the external loop begins to approach its freezing point. Automated systems reduce the circulation speed to prevent the lines from freezing solid. T plus 1 hour. External hull temperature, -100 degrees C inside the cabin, plus 22 degrees Celsius. Thermal control systems are still functioning, but efficiency is falling. To conserve power. Secondary equipment is powered down. Cameras, non-essential lighting. T plus 3 hours. Radiator temperature, -70 degrees Celsius, dangerously close to the freezing point of ammonia, -77 degrees Celsius. Critical decision. Either reduce heat dissipation, risking internal overheating, or risk freezing the loop, which would lead to total ATCS failure. The crew moves into a low activity mode, lying in their sleep stations, turning off unnecessary screens, breathing slowly. T plus 6 hours. The internal temperature begins to fall, plus 18 degrees Celsius. The crew puts on extra layers of clothing. Battery charge, 50%. Mission control calculates another 12 hours until they exit the shadow. T plus 10 hours. Cabin temperature, plus 12 degrees Celsius. Condensation appears on cold surfaces, walls, windows. Droplets of water float in 0 G. The crew wipes them up with towels to prevent shorts in the electronics. Battery charge, 20%. Critical power conservation begins. Everything is shut down except life support and navigation. T plus 15 hours. Temperature, plus 8 degrees Celsius. The crew is shivering despite 3 layers of clothes. Metabolism increases as their bodies try to generate heat, which in turn consumes more oxygen. The $CO_2 scrubbing system is pushed to its limit. Carbon dioxide concentration rises to 0.7%, ISS norm, 0.4%. Discomfort begins at 1%. T plus 17 hours. Batteries, 5%. Remaining power will last only 30 to 40 minutes. The crew prepares for the worst. If the exit from a shadow is delayed, e.g., due to an orbital calculation error, the ship will lose all power. Without power, the ATCS pumps, fans, and $CO_2 scrubbers will fail. The crew will slowly suffocate in their own exhaled breath. T plus 18 hours. The dawn. Orion exits the shadow. Sunlight floods the solar panels. Power generation is restored. 11.2 kilowatt. Batteries begin to charge. Radiators slowly warm up. The ammonia thaws. Cabin temperature slowly rises. Plus 10 degrees Celsius. Plus 15 degrees Celsius. Plus 20 degrees C. The crew has survived, but it was on the razor's edge. The reality. The Artemis II trajectory is meticulously designed to minimize time in the lunar shadow. No more than -30 to 60 minutes per pass. However, the scenario above illustrates what happens if something goes wrong, a maneuver error or an enforced delay. In orbit. Chapter 4. A 9 cubic meter prisoner anatomy of claustrophobia. The habitable volume of the Orion spacecraft is 8.95 cubic meters, excluding airlocks and equipment lockers. For comparison, standard one-bedroom apartment, -30 m3 a compartment in a sleeper train, Platzkart -12 m3 Orion for 4 people, -2.2 cubic meters per person. This is equivalent to each astronaut living in a space measuring 1.3 by 1.3 by 1.3 meters. A cube in which a person can barely spread their arms. In weightlessness, the concepts of floor and ceiling disappear, allowing for the use of all 3 dimensions. However, psychologically, humans still perceive the space as cramped, especially when 4 bodies are constantly in each other's way. The layout. Central zone, flight consoles, with 2 seats for the commander and pilot, occupies -40% of the volume. Side bays, 2 sleep stations, essentially spaces where an astronaut tethers themselves to the wall. While one can sleep in any orientation in 0G, it is psychologically more comfortable in a confined space. Lower zone, the toilet, if one can call the waste collection system that, and the food and water storage systems. The smells. Orion's ventilation system cycles air through filters but cannot eliminate all odors. After 2 to 3 days, a characteristic space smell accumulates in the cabin, a mixture of metallic notes from material outgassing, sweat, food residues, and trace amounts of ammonia from the cooling system. Even with a sealed loop, microscopic leaks are inevitable. ISS astronauts describe this as the smell of hot metal or burnt electronics. In the sealed, tiny volume of Orion, this odor will be far more intense. Physiology, life support and its limits. 1. Oxygen. An adult human consumes -550 liters of $O_2 per day, active, or -0.84 kilogram, for 4 people over 10 days. 33.6 kilograms of oxygen. Orion carries oxygen in 2 forms: compressed gas in high-pressure tanks. 300 atmospheres -25 kilogram emergency chemical oxygen candles. Lithium perchlorate -15 kilograms, generating $O_2 when heated. Total supply, -40 kilograms, providing a healthy safety margin. 2. Carbon dioxide, $CO_2. Removal. A person exhales -1 kilogram of $CO_2 per day for 4 people over 10 days. 40 kilograms of carbon dioxide must be removed from the air. Orion uses lithium hydroxide, LiOH, canisters, similar to those used on the Apollo missions. The chemical reaction is $2 text, LiOH plus CO_2. Right arrow a text vli _2 text co _3 plus h $20 1 canister weighing -5 kilograms absorbs -3 kilograms of $co $2 over -20 hours. Roughly 15 to 20 canisters are required for the mission. Once saturated, these canisters are useless. They cannot be regenerated on board. The critical point: if the canisters are exhausted early, e.g., due to increased physical activity or a mission extension, $co $2 levels will rise to 82% $co $2, headaches and shortness of breath to 85% $co $2, severe respiratory distress, risk of panic to 10% $co $2, loss of consciousness within minutes, death within 15 to 30 minutes. 3. Water requirement: -3.5 liters per person per day, drinking plus food rehydration, for 4 people over 10 days. 140 liters equals 140 kilogram. Orion carries water in flexible bladders. Some water is used in the spacesuit cooling system, which can be recovered and purified for reuse. Water recycling system: none, unlike the ISS. Every drop of water is a non-renewable resource. Conservation is critical. 4. Food -2,000 cal per person per day. Space food: freeze-dried products, rehydrated with hot water, thermostabilized pouches like military MREs, and energy bars. The challenge: in microgravity, appetite often decreases body fluids. Shift: reducing the sensation of hunger. Many astronauts lose weight during missions, but malnutrition significantly degrades performance. Zero-G sanitation: an engineering nightmare. The Waste Management System, WMS, in Orion is a modernized, downsized version of the systems used on the ISS. How it works: liquid waste: urine astronauts use a funnel with individualized adapters, different shapes for men and women, connected to a hose. A vacuum pump, creating a pressure differential of -0.1 atm, suctions the liquid into a reservoir. Urine is stored in tanks and is not recycled. The total volume over 10 days is approximately 60 liters. Solid waste: feces. The toilet is roughly the size of a large coffee canister. The astronaut must strap themselves in with thigh restraints to avoid floating away and maintain a tight seal against the seat. Airflow, again, vacuum suction, directs the waste into a replaceable container lined with antibacterial fabric. Storage: after use, the container is hermetically sealed and stored for the return trip, with activated carbon filters used to block odors. The psychological hurdle: the process takes about 15 to 20 minutes and is incredibly inconvenient. Many ISS astronauts admit that using the toilet is one of the most stressful parts of a mission. In Orion, which lacks a separate bathroom compartment, the astronaut uses a removable fabric curtain for minimal privacy. The other 3 crew members simply try to pretend nothing is happening. Psychology: the Earthrise effect and existential isolation. On December 24, 1968, the crew of Apollo 8, the first humans to reach lunar orbit, witnessed the Earth rising over the lunar horizon. Astronaut William Anders took the famous Earthrise photograph, a small, blue planet hanging over a desolate grey lunar landscape. This image changed humanity's collective consciousness. For the first time, we saw Earth not as the center of the universe, but as a fragile grain of sand in the cosmic void. Commander Frank Borman later noted, "We came to explore the moon, but what we actually discovered was the Earth." The psychological phenomenon for Artemis II. At a distance of 384,000 kilometers, Earth appears as a vibrant disk approximately 2 degrees in diameter, 4 times the size of the Moon as seen from Earth. It is large enough to distinguish continents, clouds, and oceans, but small enough to be covered by one's thumb. Cognitive dissonance. The astronauts know that the entire human race, all of history, and everyone they love resides on that tiny blue marble. They are on the outside, the only 4 human beings within a radius of 380,000 kilometers. NASA psychologists described 3 phases. Euphoria, days 1 to 2 exhilaration from the view and the realization of the moment's uniqueness. Anxiety, Days 3 to 5, the realization of isolation. If something goes wrong, help is non-existent. Earth is visually close but physically, hopelessly far away. Adaptation or depression. Days 6 to 10, the crew either accepts the situation and focuses on tasks, or begins to show signs of a depressive state, apathy, loss of concentration, sleep disturbances. Countermeasures. Regular video calls with families, though the 1+ second delay makes conversation feel unnatural. A strict schedule alternating work and rest. Group evenings, shared meals and watching movies on tablets. Access to music and books. Ultimately, the crew copes with isolation through mutual support. These 4 people become a temporary microcivilization, the only representatives of humanity in deep space. Chapter 5. The Wall of Fire, Re-entry. The most dangerous hour of the mission. Day 10. The Orion spacecraft approaches Earth. Its velocity relative to the planet is 11 km per second, 39,600 km per hour. Earth's escape velocity in reverse. TO put this in perspective. ISS re-entry speed, -7.7 km/s meteoroid speed, -15 to 25 km/s Orion speed, 11 km/s. The kinetic energy of the 9-ton crew module, after jettisoning the service module, is staggering. $E equals or frac 1 2 MV2 equals 0.5 times 9,000 times 11,000 minus 2 is equal to 544 a text, gigajoules, dollar. This is equivalent to 130 tons of TNT or a small-scale tactical nuclear warhead. All of this energy must be dissipated in approximately 20 minutes, or the spacecraft and its crew will be vaporized. Atmospheric interface, hitting a concrete wall altitude 120 kilometers. The edge of the atmosphere, the Kármán line at 100 kilometers, is fast approaching. The air density is $10 the -6 etho text, kilogram m $3, a million times thinner than at sea level. Yet, at 11 kilometers per second, even this creates significant resistance. The physics of braking. The aerodynamic drag force is calculated as $F equals O frac 1 2 a rho v2 c_da where $rho equals air density $v equals velocity $c_d. Approx $1.30 equals drag coefficient. Orion uses a blunt heat shield, intentionally creating inefficient aerodynamics to maximize drag. $A. Approx 5 text m $2 equals cross-sectional area at an altitude of 70 kilometers. A rho or approx 10 the -4 O text, kilogram m $3. Velocity still -10.5 km/s $f or approx 0.5 times 10 -4 O times 10,500 to 2 times 1.3 times 5 or approx 36,000 text. N 3.6 tons force. $. Deceleration. $A equals a frac F m or approx 4 text MOS $2 or 0 to 4G. IT sounds manageable, but as the ship descends, altitude 60 kilometers. $F or approx 350,000 text N O right arrow A or approx a math 4G. Altitude 50 kilometers. Peak heat $F or approx 2 million text N right arrow A or approx math 22G. However, the descent program is designed not to exceed 4-5G by actively managing the angle of attack. Skip entry, a dance with gravity, a simple ballistic descent, like the Soyuz capsules from Lunar. Speeds would create peak G loads of 30-40 G, lethal to humans. The solution is the skip entry, a skipping stone maneuver. The principle: the spacecraft enters the atmosphere at a shallow angle, -6 to 7 degrees to the horizon. At an altitude of 60 kilometers, atmospheric resistance begins to slow it down while simultaneously creating lift, due to the offset center of mass and the asymmetric shape of the heat shield. This lift pushes the ship back up into thinner layers of the atmosphere, -90 kilometers altitude. Much like a stone skipping across water. The stages of the skip: first dip, Altitude 40 to 60 km, velocity drops from 11 km per second to -8 km Earthrise. Peak acceleration. -4G. Heat shield temperature 2200 degrees C. The ricochet. Ascent to -90 km. The ship returns to a near vacuum velocity. -8 km Earthrise. Second dip. Altitude 30 to 50 km, velocity drops from 8 km per second to -5 km Earthrise. Peak acceleration. -3.5 G. Shield temperature 2800 degrees Celsius maximum. Final phase. Altitude 15 to 30 km, velocity drops to -300 meters per second, subsonic. Parachute deployment. Benefits of skip entry. Peak G loads are reduced by a factor of 6-8. The thermal load is distributed across 2 stages instead of one massive peak. Landing precision is significantly higher as the trajectory can be adjusted. The cost. Complexity. It requires automated attitude control with a precision of 0.5 degrees. A 2-degree error in the entry angle means either insufficient braking, the ship ricochets back into space, or excessive braking, lethal G-forces. The of-coat heat shield. Sacrificial defense. What happens when a spacecraft slams into the air at 11 km Earthrise? Air molecules in front of the heat shield don't have time to move out of the way. They are compressed to immense densities and temperatures, forming a bow shock wave. Behind this shock front, the air is heated to 8,000 to 11,000 K. For context, the sun's surface is $5,800 text K $. At these temperatures, molecules break into atoms and atoms ionize, creating a sheath of plasma. This plasma glows brighter than the sun. If you could see the returning Orion from the side, you would see a fireball leaving a trail of incandescent plasma several kilometers long. The Orion heat shield material, of coat, developed by Avco Corporation, used since the Apollo missions. Composition: epoxy resin, binder, silica fibers for structural reinforcement, and phenolic microballoons, hollow particles to reduce density. Thickness: -7 to 10 centimeters at the stagnation point, the area of maximum heating. The defense mechanism: ablation at $1 500 text degrees C $. The surface layer of coat begins to decompose, pyrolysis. Organic compounds break apart, releasing gases like $CO_2, $H_20, and various hydrocarbons. These gases escape through the material's porous structure, creating a protective layer of cooler gas between the plasma and the solid surface. Simultaneously, this evaporation absorbs a colossal amount of energy, heat of vaporization. The result: the shield's surface chars, forming a carbonaceous crust about 1 to 2 centimeters thick that is gradually eroded by the flow. However, the temperature on the backside of the shield, inside the cabin, remains below 100 to 150 degrees Celsius. The crew is safe. Material loss. During a single lunar speed re-entry, the shield loses -3 to 4 centimeters of thickness. The critical margin: if there were a crack or defect in the shield, the plasma would burn through the hull in seconds, vaporizing the crew instantly. This is why the Orion shield undergoes over 100 hours of detailed inspection before every flight, using ultrasound, X-rays, and visual scans. The plasma cocoon. Radio blackout at the peak of heating, altitude -50 kilometers, speed -10 km Earthrise. The ship is enveloped in 8000 plus K plasma. The problem: plasma is ionized gas that reflects and absorbs radio waves. All radio communication is severed. This blackout lasts for -6 to 7 minutes for Orion. Houston Mission Control sees the last telemetry at -65 kilometers. Then, silence. The crew is entirely isolated. If something fails during these 6 minutes, parachute deployment, attitude control, or structural integrity, ground specialists will only find out after the fact, when the ship fails to emerge from the blackout. For the crew, these are the longest minutes of the mission. G-loads of 4G pin them to their seats. Cabin temperatures rise to +40 to 45 degrees Celsius as infrared radiation from the white-hot shield seeps through the insulation. Outside the windows, there is a roaring orange-pink plasma glow. The noise of the shock wave transmits. Through the hull as a low howl, 120 to 130 decibels, like standing next to a jet engine. There is nothing to do but wait, teeth clenched, parachutes. The final frontier altitude 7.6 kilometers, speed 500 km/h. The parachute compartment covers are jettisoned. 2 drogue chutes, 7 meters in diameter, deploy. Their job is to stabilize the ship and slow it to -160 km/h. Altitude 3 kilometers, speed 160 km/h. The drogue chutes are released, and 3 main parachutes, 35 meters in diameter each, are deployed. These are among the largest parachutes ever used for human flight. Total surface area, -2,900 m², nearly half a football field. The shock, upon inflation, the capsule undergoes a sharp -3.4 jolt, pinning the crew into their seats once more, but in the opposite direction. The redundancy, the system is designed so that even if one parachute fails, the remaining 2 will ensure a safe landing. Splashdown speed of -10 meters per second instead of -7 meters per second. If 2 parachutes fail, the impact speed is -20 to 25 meters per second, survivable, but with severe injury risk. If all 3 fail, death is instantaneous. Altitude 300 meters. The heat shield is jettisoned to save -900 kilograms of mass. Splashdown, Pacific Ocean touching down at -7 to 8 meters per second. The capsule hits the water with a force equivalent to a 3-meter drop. The crew feels a sharp 10-15 G impact for a fraction of a second, cushioned by their specialized seats. If the capsule lands upside down, stable 2 or stable 3 position, uprighting bags inflate to flip it within 3 to 5 minutes. The crew is alive. The mission is complete. How does this flow feel for your script? I've kept the technical units like MSV, GeV, and kilonewtons intact to maintain that professional scientific edge. What aspect of the Artemis II mission should we dive into next? Conclusion: the foundation for Mars. Why Artemis II is more than just a lunar flyby. Artemis II will not land a crew on the lunar surface. In that sense, it may seem less ambitious than Apollo 11. However, from a strategic perspective, it is critically vital. 3 mission objectives. Validation of Orion systems in deep space. While Artemis I, 2022, uncrewed, tested the spacecraft, automation cannot simulate the human factor. The Artemis II crew will. Validate control interfaces under stress. Test life support systems under a real biological load. Perform manual maneuvers in case of automated failure. Evaluate the psychological endurance of a long-duration flight. Preparing for Gateway, the Lunar Orbital Station. Artemis III and subsequent missions will utilize the Lunar Gateway, a station in a high elliptical lunar orbit. The Gateway will serve as a staging base. Orion delivers the crew to the station, and from there, the Starship HLS, human landing system, descends to the surface. Artemis II will practice simulated rendezvous maneuvers, navigation, and deep space communication, all skills necessary for Gateway operations. Radiation data for Mars missions. A Mars expedition will take approximately 900 days, 270 days each way, with 500 days on the surface. The crew would receive a radiation dose between 600 to 1,200 MSV. Artemis II will provide 10 days of invaluable data on the physiological impact of GCRs and SBEs. This data will refine risk models for cancer, cataracts, and cardiovascular disease, potentially leading to new countermeasures such as pharmacological radioprotectors or improved shielding. The philosophy of the frontier. Why go to the moon when there are problems on Earth? This question was asked in the 1960s, and it is asked today. Why spend billions on space when Earth faces hunger, disease, and climate change? There are pragmatic answers: technology spin-offs, GPS, advanced materials, medical imaging, inspiring a new generation of scientists, and fostering international cooperation. But there is a deeper answer. Humans are an exploring species. We left Africa 70,000 years ago not because we ran out of food, but because of an innate drive to see what lay beyond the horizon. We crossed oceans in fragile boats not because there was no room left, but because we had to know. We climbed Everest not for treasure, but because it was there. Every frontier we cross, geographical, technological, or intellectual, expands our understanding of the possible. The moon in the 1960s seemed unreachable. Then it became, briefly, routine. Mars today seems like a fever dream. In 50 years, there may be children living there for whom Earth is simply the old world. Artemis II is a bridge between the heroic but brief Apollo era and a new era of permanent human presence beyond low Earth orbit. It is a test that will prove we can protect fragile human life from the radiation, vacuum, and cold of the void. We can send humans into the abyss and bring them back alive. When the 4 Artemis II astronauts emerge from the capsule after splashdown, drenched and exhausted, but alive, they will bring back a fundamental truth. The next step is possible. The moon is the proving ground, Mars is the goal, and the goals beyond Mars, the asteroid belt, the moons of Jupiter, the Oort cloud, await. Frontiers exist to be crossed. Artemis II is crossing one of the deadliest borders humanity has ever known, and this is only the beginning.